Hello, everyone. I am pleased to welcome you to my presentation on AdaDrive, Self-Adaptive Slow-Fast System for Language-Grounded Autonomous Driving. I will structure my presentation into the following sections: Introduction, Methodology, Experiments, and Conclusion. The first generation of LLM-enhanced autonomous driving approaches employ a synchronous structure, where both LLM and planner operate at each driving step. While these models improve driving intelligence, they introduce substantial memory overhead and latency, making real-time deployment challenging. Generation 2 methods implement asynchronous processing paradigms, utilizing distinct but predetermined activation frequencies for the LLM and planner. However, these fixed schedules greatly limit model adaptability, as the need for LLM intervention varies significantly across different driving scenarios. For instance, in safety-critical situations, LLMs may not be invoked when they are needed most. Conversely, in simple scenarios, activating LLMs may be unnecessary, leading to suboptimal resource utilization. Given these limitations, we believe that an ideal LLM-enhanced autonomous driving framework should be able to dynamically decide when to activate the LLM and adaptively control the degree of LLM influence. To address these challenges, we introduce AdaDrive, a next-generation self-adaptive LLM integration framework for autonomous driving. Our proposed AdaDrive also employs an asynchronous architecture but features two novel adaptive connectors, Connector W and Connector H. Connector W for adaptively determining when to activate the LLM. Connector H for controlling how to integrate the LLM in driving tasks. Besides, we also incorporate LSFormer for efficient processing of continuous streaming data. Let's dive into the details of our method. AdaDrive leverages a slow-fast system paradigm to balance high-frequency low-latency tasks and low-frequency high-reasoning tasks. Our framework consists of a shared multimodal feature extraction that encodes the vision input and vacation instruction. A fast path employing a lightweight planner without invoking the LLM for high-frequency, low-latency tasks. A slow path utilizing an LLM as a cognitive agent for low-frequency, high-reasoning tasks. Most importantly, the key component, our adaptive connector, automatically manages transitions between slow and fast paths depending on driving situation. Given the current driving context feature, we predict a confidence score that determines the LLM's activation utilizing an MLP function. And then, the continuous probability distribution is transformed into a discrete binary decision through the Gumbel softmax, which ensures end-to-end differentiability by maintaining the gradient flow. The implementation of Connector W is straightforward, but the optimization presents significant challenges due to the absence of gold standards or ground truth supervision signals for optimal activation timing. In our work, we propose a novel comparative learning-based adaptive activation loss to address these issues. Specifically, in our work, we perform two forward passes for trajectory prediction, one with LLM assistance and another without. And then, we calculate the trajectory loss for the two trajectory predictions, respectively. Their comparative difference reflects the magnitude of LLM's contribution to trajectory prediction at the current time step. Finally, we link the binary decision with the trajectory losses to construct a novel adaptive activation loss. Optimizing this objective function naturally induces pi-t equals 1 when the LLM loss term is less than the non-LLM basic loss term, and 0 otherwise, thereby enabling the model to learn optimal LLM activation conditions. Further, to achieve optimal performance gains while minimizing computational overhead, we introduce a penalty term gamma into the LLM-assisted trajectory loss to control the frequency of LLM activations, ensuring LLM is only activated when LLM loss term is significantly lower than non-LLM basic loss term by a predetermined margin. Upon LLM activation, Connector H modulates the contribution of LLM features to base features by leveraging the prediction confidence as a dynamic weighting coefficient. Thus, the trajectory prediction can be uniformly formulated as this formula. We utilize the official language-driven autonomous driving dataset to train our model, and conduct experiments on the Lang Auto benchmarks on the Carla simulator. Experimental results demonstrate the effectiveness of our method. We also compare our adaptive LLM activation strategy against fixed-interval activation at various frequencies. Furthermore, visualizations are provided to demonstrate the LLM's activation frequencies as well as the associated driving scenarios. Finally, we come to the conclusion. That's all for our presentation. Thank you for your attention.